Good morning. We're about to start a brand new chapter, Unit 3, over number theory. One of the big ideas in number theory is prime numbers. So to understand prime numbers, we have to talk about composite as well as some rules for divisibility that are super handy. So I don't think you're going to hear anything completely brand new to you, but it'll be a good reminder. So let's navigate around just a little bit. First, I've given you a definition of a prime number. A prime number is a number that can't be divided evenly by any number except for itself and 1. That's one way to define it. I've given you several examples here. As numbers get larger, it's a little harder to determine if they are prime or not. Well, typically people like to think that if it's not prime, then it's composite. Well, that's not wholly true. It's a composite number when it can be divided evenly by numbers other than 1 or itself. There's a couple of special numbers we'll talk about in a minute, but not every number fits into one of these two categories. Let's look at another example. For example, the number 18. It's composite because 18 can be divided evenly by 2, 3, 6, and 9, not just 1 and 18. If only 1 and 18 were factors of 18, then we would call it prime. So then I've written out 12. 12 can be divided evenly multiple ways, so it's another composite number. So any whole number greater than 1 is either prime or composite. Now that's a true statement. So 0 and 1 are neither prime nor composite. That's something to remember. Let's go to page 2 of your handout. Oops, I went the wrong way. There's another way to define a prime number, and that's by using different terminology, talking about its factors. So we've shown that the number 6 can be written as a product of 2 times 3. So these numbers that you use to multiply together to get something else are called the factors. So when the only two factors of a number are 1 and the number, then it's also prime. Just a different terminology there. It means the same as our previous definition. And just remember that we're only talking about whole numbers here when we refer to prime or composite. So we're not talking about the fractions or negative values. Just actually, whole numbers start with 0, but this says 1, 2, 3, etc. That's just because 0 can't be a prime number. So you might be thinking, well, what is all the fuss about prime and composite? Well, there's actually a big deal with prime numbers. They're basically the building blocks of all numbers. All composite numbers are made up of prime numbers, which is where they get their name composite. That's a composition of other things. So down here is a good example. If you take these prime numbers, 2, 3, 5, and 7, they can be used to create a composite number. Like 2 2's multiplied together will give you the composite number 4. These two prime numbers, 2 and 3, their product is 6. 5 is prime. 8 is composite because 3 2's multiplied together makes up 8. 2 3's makes up 9, and so on. So every number that's composite can be expressed as a product of primes. So here's an example, 12. 12 can be made up by multiplying these prime numbers, 2 times 2 times 3. Just if a factor is repeated, that's not a problem. It just means that 4 is a factor, and we split it up by writing 2 times 2. We would use our exponential notation and write 2 squared times 3. And we'll do more of that in another lesson. Now we're going to talk about the divisibility rules. The divisibility rules may or may not be something that you've heard of before. Some of them for sure, but some of them may be new. The divisibility rules just help us determine if numbers are divisible by another, meaning a number is divisible if it divides evenly. In other words, no remainder. So one of the rules, here's just a quick example. The rule for 3 says if you add up all the digits of the number, if that number is divisible by 3, then the other number is divisible by 3. So if you add 7, 2, and 3, you get 12. 12 is divisible by 3, so 723 is divisible by 3. All the rule does is tell you if it's divisible or not. It does not tell you the missing factor, like 3 times what is 723. You would have to use some division to get that. So let's take a look at our list. Well, obviously, every integer is divisible by 1. This one is one most students are familiar with. You could either think of it as if the number is even, but a number is even if its last digit is even. And it has to end in 0, 2, 4, 6, or 8 for that to be the case. So you've got an example and a non-example. The rule for 3 is really one of the handiest ones of all. I would actually star that one over here. That is the most pathetic asterisk ever. That's okay, it serves its purpose. So there's a couple of more examples. 381, 3 plus 8 plus 1 is 12. So yes, it's divisible by 3. 217, that adds up to be 10. 10's not divisible by 3, so no. This is the interesting part right down here that I'd never really thought about before, but this rule can be repeated. So for example, this is a really big number. So when you add it all up and you get 42, say you don't know if 42 is divisible by 3. Well, then you could just add up 4 and 2 here, and you get 6, and that's divisible by 3. So that means 42 is divisible by 3, which means 99,996 is divisible by 3. That is super cool. Super handy. I love math facts that are super handy. The rule for 4, this one seems to be one that, I don't know, for some reason, okay, I'm trying to erase, my gosh. Please don't laugh at me. Okay, let's get back together. 4 is just one I found that students have a hard time remembering. I'm not quite sure why. But you don't add anything up. You merely look at the last 2 digits of a number. If the number formed, not the sum, but formed, is divisible by 4, then the entire number is divisible by 4. So you see here 12 is divisible by 4, but right here 19 is not. So 7,019 is not divisible by 4. I like this little quick check that this resource gave me as well. I'm going to star that. If a number is divisible by 4, then if you take half of it twice and the result is still whole, then it's divisible by 4. So half of 12, 6, half of 6, 3, still a whole number, so yes. Take half of 30, you get 15. Take half of that again, well, 15 is not even, so you're not going to be able to take half of it again and get a whole number, so it's no. So that's just like a little alternative when you have a smaller number, whereas you don't have anything to just look at the last 2 digits. 5 is actually one of those that students typically know. If a number ends in 5 or 0, then it is divisible by 5. So that one's pretty easy. We like that one. 6 is, it's got to be even, which means it's divisible by 2, and it's got to be divisible by 3. So you're just applying 2 rules that we've already learned. 308, it's even, but 3 plus 8 is 11, and 11 is not divisible by 3, so 308 is not divisible by 6. Now the rule for 7, I generally don't use it very much, but I do think it's interesting, and I probably should learn it, so I'm actually committing this one to memory, and it's really sort of fun to do. You double the last digit and subtract it from the number made by the other digits, and that result has to be divisible by 7. And then again, you can apply that rule again if you need to. So here's how it works. They show it really well here. If you double the last digit right here, 2, you get 4. So let me kind of circle it. 4. Okay, that was a bad idea because now you can't see the rest of it. Let's try the highlighter. Okay, so right here you double 2 and then you get 4, and the number that you have left over there, 67. 67, you subtract the 4 from it and you get 63. Well, 63 is divisible by 7, so that means 672 is divisible by 7. So takes a little time to get used to. So we double 5, subtract, that's 10, subtract that from 10, and that's 0. Remember, 0 is divisible by any number. 905, double the 5, that's 10, subtract it from 90, that's 80. 80 is not divisible by 7. We know that just from our multiplication facts. Let's keep going. 9, the rule for 9 works very much like the rule for 3, and this one is a good one to put an asterisk by as well. This time the sum of the digits just has to total up to be something divisible by 9. So 1629, if you total them all up, you get 18. Well, 18 is divisible by 9, but if you didn't know that, you could add 1 and 8, applying the rule again here, and that's divisible by 9, so that means 1629 is divisible by 9. The rule for 10, of course, everyone knows really well. If a number ends in 0, then it's divisible by 10. So the rule for 11 is not a rule I have ever learned before, but I'm just marking up my whole thing. Just ignore me, kids. It's okay. Just Miss Shaw winging it through the video here. I like the rule for 11, and I realize it actually is really pretty handy. It beats going over to the side and doing long division to decide if 11 divides into it. Now, we know, up to 11 times 12, which is 132, but when you get numbers bigger than that, you might not know. So this one's not too bad, but it sounds kind of weird. You subtract the last digit from the number made by the other digits. So that's a lot like the rule for a 7, except there's no doubling. So I'll subtract 6 from 28, and I get 22. Well, 22 is divisible by 11. So that's pretty handy. That would tell me right off, that would help me possibly in something we're doing later with prime factorization. There's reasons why that would be handy. Here's a much bigger number. So notice how you can keep going on this one. If you subtract 1 from this whole 4-digit number in front of it, you get 1463. So now if you subtract 3 from 146, you get 143. And then if you subtract 3 from 14, you get 11, which is divisible by 11. So we know 11 is a factor of 14,641. And there really are a lot of other rules. There's actually a lot of divisibility rules for larger numbers and more tests for even the ones that I've shown, but these are the most useful and commonly used rules. So the rules can help you determine if a number is prime or not. So let's take a look at some examples here. if you want to try these by yourself and then come back to the video, it's not a bad idea. So when I look at a number right off, just because it's not in your multiplication tables doesn't mean that it's prime. So you know it's odd, so it's not even, so it's not divisible by 2. The next thing you would always try is see if it's divisible by 3. Well, 8 plus 7 equals 15, and 15 is divisible by 3. So I'm just going to write over here, so divisible by 3. So that makes it a composite. I'll just put a C there. And when you get to 31, you probably recognize 31 as prime already. If you try the rules on it, it's not in your multiplication facts and it's small, so unless it's divisible, like a number like 13 or something like that, numbers that are not in our multiplication facts, then those slip through the cracks sometimes. But 15 goes into 30. 13 times 2 is 26, so those numbers just don't go, so this one is prime. You got to be really careful about trying to quickly decide if something's prime or not when it starts getting bigger, something like 549 right here. So we would just have to try some different things. I'm not quite sure if it is or isn't, but it's not divisible by 2 because it's not even. Let's see if it's divisible by 3. 4 and 5 is 9, plus 9 is 18. So I'll just write over here the sum of the digits equals 18. So that tells us that it's divisible by not only just 3, but also 9. And there could be other factors, but as long as we find factors other than 149 and 1, then we know it's composite. Scroll down, see if I can keep from writing on the page. Oh, nope, couldn't do it. 781. Let's look at 781. Right off, when you add 7 and 8, you get 15 plus 1. That's 16. So it's not divisible by 3. It's not divisible by 2 because it's not even. It's not divisible by 4 because 81 is not divisible by 4. It's not divisible by 5 because it doesn't end in 0 or 5. Let's try that little rule for 7. It says if you double the last number, which is 2, and subtract it from 78, you get 76. Well, 76 is not divisible by 7 because we know 77 is divisible by 7. It's not divisible by 9 because 16, the sum, is not divisible by 9 or 10. So then you have to kind of get up to some bigger numbers. Let's try the rule for 11. Remember, 11 says you just take the last digit, subtract from this number here. So that gives us 77. Oh, so 77 is divisible by 11. So this number is divisible by 11. So that makes it composite. All right, let's try 589. Just take a minute, pause the video, and go through each one of your divisibility rules. And I'll be right back. Okay, well, I've just kind of shown over here to the side what I've figured out about all of these numbers that we have rules for. And I kind of showed a little work, and hopefully you figured out the same thing. But just because you get through 11 and none of those work, you cannot conclude that this number is prime. Unfortunately, then you have to start trying some of what I like to call the ugly numbers, like 13, 17, 19. Those are numbers that sometimes will go. So we'll just come over to the side, do a little scratch work. It's inevitable sometimes. Let's try the ugly 13. And we just did long division in our last chapter, so it's good practice. So 13 into 58. If you're a card player, you know that's 4, because there's 4 suits in a deck of cards, and there's 52 cards in the deck. So there's 13 diamonds, 13 clubs, 13 hearts, and 13 spades. So you subtract. I digress. Now 13 into 69. Let's see, does that go evenly? Let's see, what's 13 times 5? That's going to be 65. Okay, so that's 65. So no, this isn't going to work. So it's not 13. So let's try. Sorry. Let's try something else. We know it's not going to be 15, because then it would end in a 5 or a 0. But let's try, what do you want to try, 17? And I know it's not pleasant, but a lot of things in life are not pleasant. But we'd have to do them anyway. 58 minus 51, that's 7, bring down the 9. 17 into 79. I know 17 times 2 is 34. So 17 times 4 is 68. That gives us 11, so 17 is not going to work. Well, let's try 19. Don't poop out, kids. Change colors, try to keep it interesting for you. All right, let's try 19. So we've got 589. So 19 times 2 is 29. No, 19 times 2 is 38. So 3 times. Oh, it looks like we're going to have a winner here. We bring down the 9, and 19 goes into 19 once. And that's 19. No remainder. Ta-da! So, we'll back it up just a little bit here. So this one is composite. This is one where a lot of people would kind of give up and get a little wimpy, get a little tired, and just settle for writing an answer down. So you really have to think. You know, something I realized I didn't talk about that was in your notes, and I'm flipping back just really quickly, was, let's see where it was. Oh, gosh. Where? One of the things I wanted to talk about, it looks like I'm missing a whole page. No, right here. I didn't point this little paragraph out, but this is really interesting. It says there's many puzzles in mathematics that can be solved more easily when you break up the composite numbers into their prime number factors. And this is what I thought some of you might find interesting. I know I do. A lot of internet security is based on mathematics of prime numbers. So if you have an interest in becoming a hacker for good, to use your skills for security purposes, you would be studying more and more about prime numbers. A lot of computer language involved in prime numbers. Well, that is a wrap for lesson 3.1, and have fun with your homework.